I don't think so. It's not here. So good morning, everyone. So today I'm going to talk a little bit about this project we've been working on, which is associated of applying evolutionary algorithms for superconducting qubit design. So throughout this presentation, I want to start with some refreshing about superconducting circuits, as we have many different backgrounds. So I just explain a little bit so that everyone can. So I'll try that everyone can follow along the presentation, even if you don't work with this topic. Then I'll motivate why using this platform, why it's flexible, and why it's interesting. And I'll continue by looking at the characteristics that makes a good qubit, and we'll try to make something with that. So in order to motivate what is a good qubit, I'll talk a little bit about noise protection. And to finish, I'll explain some results we've had and some remarks. So to start with, some little bit of recap about superconducting circuits. So I don't know how many of you are familiar with superconducting circuits, but they are just regular circuits, but they are made of superconducting materials. So why using a superconducting material? These are materials that have some special properties when cooled down certain critical temperature. So these, the main characteristics of these materials are they expel a magnetic field and they present no resistance to DC current. So essentially these characteristics are quantum properties of the system. So basically these kind of devices allows us to observe quantum properties in essentially macroscopically sized devices. So essentially, if you take a superconducting circuit and look at it, you can see it in the chip. As I mentioned, they are just regular circuits, so they have like regular components from a regular electric circuit. We have capacitors, inductors, and then we have like a special element, which are Josephson junctions, that are just non-linear inductances. They are inductances that depends on the superconducting phase between the superconducting islands. The expression is here. So if you worry about the physical implementation, they're just two superconducting islands separated by a piece of dielectric. And so these kind of elements are arranged in this kind of structures, just like regular electrical circuits. And here I put an image of a real device, a transmon here. And here we can see that we have two islands. They are coupled together through a junction, one of these components. And here the variables that we care about are the difference of charges between these islands, which is represented with this operator n, and the difference of the superconducting phase, which is represented with this operator phi. So basically, I want to explain the most simple example, which would be this kind of circuit, just two superconducting islands separated by, connected by these three elements. So each element will store energy. We have the capacitive energy, the Josephson junction energy, and the inductive energy. So this is the Hamiltonian representing this system. Apart from this element, we can see that there's two extra contributions, the n sub g and phi sub x. These are the external contributions. These account for charge differences between an external charge difference induced between the superconducting islands and an external magnetic field threading the loop formed in the circuit. So this Hamiltonian, although apparently simple, it has many different behaviors. So we can see that if we set this Josephson junction to 0 and we, with these two being non-zero, we have the quantum harmonic oscillator, which is just a linear system where the energy difference between levels is the same. So it's basically insensitive to external magnetic fields and to charge noises. But however, if we change and we set this inductance energy to 0 and we keep this Josephson energy big and bigger than the capacitive energy, we have the famous transmon qubit. So this is just a weakly nonlinear system. Now the difference in energy between the levels is no longer the same throughout all the spectrum. And we have the the energy between the transition 0, 1 is different from the rest. So this device is insensitive to external magnetic fields. We can see that we are reusing this term here. But however, it has dispersion. It's affected by this kind of charge difference between islands externally induced. So we have some dispersion. But the fact that we make this bigger than this makes that this error is like this disturbance is smaller. And also another possible arrangement of these three energies is the one shown here. So the just some energy bigger than the capacitive energy and inductance energy. And this kind of device is called the Fluxonion device, which is also pretty famous. This system is highly nonlinear and is sensitive to the external magnetic field, but not to the, has no energy dispersion due to static charge noises. So with this, what I wanted to show is that with this really simple system, which is basically a single mode circuit, we have like completely different behaviors, and we have a lot of different combinations that we can reach, and a lot of different quantum systems that we can engineer with different properties. So here, I just mentioned three, but there are a lot of them. So here this is an image from a paper from Matilda Peruso. And here they show that with different relations between these energies, we have different devices with different characteristics. And people have been working on this a lot and have developed like a lot of different superconducting qubits with different coherence times, but just with one single mode. So basically, using only one degree of freedom. So now, let's think, what about if we include several modes into the system? So if we include several modes, we'll have a lot of modes or relations between energies of our system, so we can essentially have a lot of different behaviors. And what about if we arrange it in different ways? What about if we mix them, we arrange it like this, or like this? We'll get a lot more different behaviors and a lot of different characteristics. So what is the problem then? So basically, when we get a lot of modes together, the theoretical description gets a little bit cumbersome, and it's difficult to make an understanding out of it. Also, we have so many different combinations that it's hard to know what combinations are the ones that are interesting or the one that matches certain characteristics. And also, it's computationally hard to compute these kind of devices because as more modes you add, the computation is harder. So what can we do about it? So can we find a way to find a superconducting circuit of several modes that exhibits characteristics that we are interested in, into? So for that, we can think of classical optimization methods just to find these values of EC, EL, and EJ for different arrangements. But the problem is, where do you start? If you don't know what kind of energies give rise to certain characteristics, it's difficult to find a way to start. That's why we are employing evolutionary algorithms. So these kind of algorithms are population-based. They evaluate many circuits at the same time. So they are great for exploring large parameter spaces. And they are able to find like fast local minimums that matches approximately your characteristics. Also, these kind of algorithms are based on recombination. So you take two good circuits and you combine them to create a better one, which is kind of interesting. And with this property, you can play a lot with it because you can find like clever ways to recombine the circuits in order to have better ones. So this is the algorithms. I'm not going to go into more details about this. I've already talked about this in a previous talk. And so now let's see if we can use these algorithms and this flexible platform to find a multimode circuit that works as a good qubit. So our goal now is to find a multimode circuit with proper characteristics to work as a good qubit. But first, what are those characteristics? So we don't have to think about it much. There's Di Vincenzo who provide us with the criteria for a system to perform quantum computation. So The first one is we need to find a scalable physical system with well-characterized qubit. So the scalable part, we'll talk probably in another, I'll speak about it in another talk, but now we want to care about the well-characterized. This well-characterized part, we can translate it into having a system where the anharmonicity between the computational states and the rest of the spectrum is large, so we have large anharmonicity. Then we also need the ability to initialize the states of the qubit to a simple state. This can be achieved in superconducting circuit by cooling the system. So as far as we keep the frequency of our qubit larger than the thermal frequency of the qubit, at the temperature that we are working on, we can like make sure that when we cool down the system, it's going to go to the ground state. Then we care about having long decoherence times, so we care about noise protection. It's what I'm going to discuss now. And we also need a universal set of quantum gates. So we also need the system to be affected by external drives. Yeah, you have a question?
Before we continue, because I think I'm losing one thing. If you have both qubits, you have two modes.
Yeah.
You have all the stuff. Okay, how are they connected? Like they should be like.
They are coupled, yeah. So here, basically, you have like components like this connected to other components,
But it's like a double wall potential, or is a single potential?
It's multidimensional potential. I mean,
and they are connected like this makes like the Hamiltonian connected to the two modes.
yes, the Hamiltonian is connected between the two modes. So you will have like several variables, several modes over here, and they will have a potential. They may be uncoupled or may be coupled. Maybe the potential part is coupled one from another. So the values of one mode modify the potential of the other mode.
Because interesting to create a bigger Hilbert space. Like why
you create a bigger Hilbert space.
This is why you want to make a multimode.
Yeah. Yes. Yeah, the motivation is to reach more different characteristics and properties and behaviors.
And it's like two, well, it's the same. Yeah.
Okay. So yeah, now I want to address this problem over here. Now, large anharmonicity is clear. We need the first two, the energy difference between the computational states to be different from the rest of the spectrum. We need the qubit frequency, which is clear. So I'll elaborate a little bit more on noise protection. So the theory, a little bit of theory about noise protection. So essentially, we want to encode our quantum information in this kind of superposition states. So here we have an amplitude, which is kind of this difference between the amplitude between these two computational states, and also we have a phase between the computational states. So here we can differentiate bit flip errors and phase flip errors. So these kind of bit flip errors are errors that affect the amplitude between the computational states, and they define our depolarization time T1. However, there's also these phase flip errors which affect the phase between the computational states and define our pure dephasing times here. With these two time scales, we can define the overall total coherence times of our system like this. Yeah, we have these time scales, but how are defined and how are these time scales related with the errors that affect our qubit? So the main errors that affect our superconducting circuits are essentially these ones. So charge bias and external magnetic field bias. These are the errors that I've already mentioned, like the external effects that I've already mentioned before. So essentially we have this charge bias. This error is coupled to the system through this operator, the charge operator, as is an extra charge difference between the islands. So the Hamiltonian representing this error would be this one here. The external drives modifies the phase difference between these islands and is represented with this one. So the crucial expressions here that relate these kind of errors with depolarization times and pure dephasing times are over here. So basically this tells us that the depolarization time is going to be proportional the evaporation rate is going to be proportional to how strongly the noise couples our two computational states. And the pure dephasing time the rate of pure dephasing time is proportional how this noise varies the frequency of our computational states. Also, here in the expression, we can see that we have an extra term that I will not speak a lot about. This is the power spectral density of the noise source. This is a parameter that we don't have access to theoretically. It's more like it can be improved using noise filtering, filtering the qubit from the environment a lot. So this is more on the laboratory side. But of course, if we want to improve these times, we can try to engineer these two aspects over here. So then to find a circuit with long coherence times, we need a small matrix elements coupling the two computational states, and also systems that vary, the variation of the energy due to this noise is small. So finally, we've arrived to have all the characteristics we are interested to have in our system so as to work as a good qubit. So we need a large harmonicity, we need this transition 0,1 to be larger than the rest of the transition of the spectrum or to be smaller. We need the qubit frequency to have a frequency above the thermal frequency. To reach noise protection, we need to minimize these matrix elements of the matrix elements that couple the two computational states from the noise operator, and also to minimize the variation of the transition frequency between the computational states due to these external errors. Finally, one thing I've not mentioned much, but we are also, despite needing this to be small, we cannot make it zero because we still need to be able to address this transition using external sources. So we need to minimize this, but keeping these matrix elements different from zero, because yeah, the noise source affects, it's coupled through the system through the charge operator, but we also drive our system through the charge operator. So we are interested in minimizing this, but also being not zero so that we can still drive our system. Yeah, you have a question?
What imposes like the lower bound on that?
The reference we've been having is trying to minimize the matrix elements that we know that are too much. I mean, for example, we have it's a really limitation in transmons, which have 1.6, for example. So we're trying to make this smaller, but if you make it zero, which is what happens in the 0-pi and all these kind of protected superconducting circuits, you cannot address simply the transition. So you have to like make weird things to apply single qubit gates, like go to higher computational states and then go back.
So what I mean is, like, what's the scale to consider that matrix element zero?
Yeah, that's kind of difficult to answer because it depends on the device. This is a dimensional. How much? What?
How much power?
Yeah, how much power can you input? If you make it really small, of course you can. It's not zero. If it's not zero, you can always make the gate, but you will need a lot of power or a lot of time. So, for example, with 0.5 matrix element of 0.4, you can have relatively fast gates with the power you can achieve. Okay.
One question.
Yeah.
So this error on the left, the one with the charge operator. This one. This thing. So this is due to
Static magnetic fields and static charges.
Okay, and let's say the noise which is on resonance, you consider it's so low because of the second condition, right?
Yeah, you want it to vary. Yeah, the derivative at the working point should be smaller.
Ensures you that you have non-resonant noise, right?
No, but this is like so as to the thermal excitations don't affect your qubit, but this is not the same. This is, for example, charges that extra electrons or extra Cooper pairs that get into one island. so as that they don't modify your system characteristics, basically. Okay.
This is that all this that you have to generalize the more states that you go to if you use a multimode because it's for a single cube. But if you have more modes, because later.
Yeah, but we are encoding the computational states into the whole system, into the multimode device. So you're looking at the global eigenvalues. So it's a combination of all modes. But when you measure one energy, that's it.
When you go up in a level in the system, so you go from the 0 to the 1 state, this excitation has something to do with an extra charge or something with the phase, or is it?
No, it's an extra, it's a driving that you have in your system. So you drive it with a microwave source. So basically you have your transmon here. Here, you see that here there is a cable that goes to the island. So essentially you send microwave signal here and you drive so as to have like so as to provide energy and create an excitation.
Okay. But this exciting the qubit doesn't change the charge or the phase?
Yeah, I think it changes the charge. You change to a different state.
Okay, I can understand more.
You have an extra excitation. I mean, you have 0 excitations or 1 excitation.
And this increases the charge?
Yeah, but for example, here you can, in superconducting materials, the charges are Cooper pairs. But you can also have single electrons that are dissipative, but they can exist there. So if you have, because of the environment, an electron appears here, an extra electron, you want your system to be resilient to that, and the energy to not vary due to that.
When I drive, am I introducing Cooper pairs or am I doing a different thing?
You
How
intro
do I drive? What is my driving?
a microwave, a sinus, a sinusoidal signal.
It is proportional to the flux or something like that?
To the charge in this case.
So my degree of freedom in order to drive is the charge.
Yes. I mean, you can also charge. You can also drive with the phase with an external magnetic field, but just maybe a little bit harder. Okay. So yeah, now I wanted to present some results. So we ran the optimization, and we obtained this weird thing here. This is just a four island circuit. So we essentially have 3 modes. These are the values, which are kind of weird, but we keep them realistic so as to be possible to implement them in the experiment. So from this device, we can see that first, the harmonicity it's good. So we have a transition frequency of 1 gigahertz with an harmonicity of 300 megahertz. You can see that the limiting factor is not the transition between 1 and 2, but the transition between 1 and 3, which is the most limiting factor. So we have this frequency with this qubit anharmonicity, and we can also see that we have reduced matrix elements, which are like much lower than in transmon cases. So we expect this system to have better T1s than transmon. So if we look at the noise protections, we see that this device has a dispersion due to external fluxes. Here I plot the eigenvalues and the effect of the static external magnetic field applied to the system. We can see that the sweet spot of 0.5 flux quantum, there is dispersion, but this dispersion over here is around 4 megahertz, which is like 2 orders of magnitude smaller than fluxonium. And we also have charge dispersion, which is around of the value of the state-of-the-art transmons that people are building now, which is around 40 kilohertz. Okay, so from this device, we see that it is sensitive to both external charges and external fluxes, whereas the transmon is only sensitive to charges but not fluxes, and the fluxonium is the opposite, is sensitive to fluxes but not charges. This is sensitive to both, but we can see that it has better dispersion than fluxonium and are on the same or better dispersion than transmons. So it's a mixture of them, but if we achieve better dispersion than both of them in both, it should be a better device. So now comes the problem of if we have a result from an optimization, it can be a random capacitance matrix with random values of the capacitance, inductors, and Josephson junctions. So can we build that realistically in an experiment? So this is the question I worked on during my stay in WMI. So essentially, the most important aspect of our circuit is if we can make the capacitance matrix, the capacitive relation between the islands possible in an experiment. So for that, first we looked for a fast way to compute this capacitance matrix out of geometric designs. So we generate this kind of designs and we parameterize them and generate like a mesh to be able to simulate it using FEM simulation, finite element method simulations. We decide norms to compare the matrix, and we used different optimization methods to try to find the optimal values of these parameterized designs that matches the capacitance matrix we're interested in. So for this device I showed you before, we've been working a bit on that. So this is basically the target capacitance matrix we want to obtain. And these are two of the parameterized layouts we've been using. So essentially here we have 3 islands and 1 island which is surrounding all of them. Here we can vary like the width of these arms, the length of the arms, but of course we have to take into consideration the fabrication constraints. I mean, we cannot introduce a junction if the space between islands is smaller than 20 micrometers. Also, we included the chip size that they can work on, which is 800 micrometers. So we ran the optimization and we obtained this capacitance matrix. This element is a little bit weird. This is a fail from the simulator, but we can look at the coupling. These values over here represent the coupling between different islands. So we have island 0 and the coupling between island 0 and 1, 0 and 2, 0 and 3. And well, it's symmetric, so we have the same. So each of these values represent the coupling of each island to the others. So we need to find a geometrical layout that matches this capacitance matrix, and this is how good we can approximate for now. We computed this with this approximated layout, the properties of our system, and it's basically the same. But it has a little bit more charge dispersion, around 200 kilohertz, which is also more or less the dispersion that they have in their transmons. And this is due to the fact that these capacitance over here, these 3 capacitance over here, are smaller than the capacitance that we have over here. So this is, if the capacitance is smaller, it causes more charge dispersion. So some final remarks. These presentations, I wanted to show you a little bit how flexible this superconducting circuit platform is. Then we address the problem, the optimization problem of finding a good qubit, the characteristics and what makes a qubit good. So then I presented a result from the optimization we've been doing. And I show you that this design has large harmonicity, has reduced matrix elements compared with other devices, which can reduce the effect of charge noise into our device, increasing our T1s. And also, I've shown you that has reduced dispersion due to both static and charge fluxes, which can increase the dephasing time of the device. And that's it. Questions? Fluxmon. Fluxonium and transmon.
Okay.
Maybe a question about the work you have done, because what is more difficult, to design the topography of the circuits, or to design the optimal lithography map for that to then to build it?
Yeah, I mean, it's a combination of both, because first we have to find realistic values for the physical parameters. So people tell you, we can make from this to this, but in fact, if you have the chip size of 800 micrometers times 800 micrometers, you can reach, if you have two islands, of course, you can reach capacitance of like 70 femtofarads. But if you want to have 4 islands inside there, the capacitance you can reach between every island is like 30 femtofarad. So you have to like try compute capacitance energies from these layouts to see what are the real parameters that you can achieve, and then use these parameters, these capacitances that you can reach, to put it into the first optimizer and optimize the theoretical description.
Yeah, because I also guess that the family of shapes they can do with lithography is not infinite, so you cannot do some random stuff, like maybe do some like paint to increase the.
Yeah, but yeah, there are more constraints to this. I mean, I know nothing about lithography construction, but for example, this kind of interdigital capacitors are not so good when implementation-wise, for example, because of the magnetic fields and so on. So yeah, there's more into this than that. So they also more rounded shapes are better. So here is like too much of square, and we have to improve. It needs to improve. It was just like a proof of principle that we can build these devices in this. So just to make it better, we just need to make it better. But
yeah. It's very difficult to optimize.
So optimize it.
Yeah, it sounds very, very, very difficult for me.
Well, the funny thing is that the other day I spoke with these guys, and they can build like the laser can have 1 micrometer precision. So you can make blobs and you can make weird shapes. You can make here basically nearly whatever you want. Of course, these kind of things, the small, makes the electric field to make weird things here. And this causes like more losses into the dielectric and more dissipation and more problems. So you have to make it round and smooth.
Yes, the corners are bad.
Corners are bad. I mean, they are rounded, but here you cannot see it.
And what is this Schumillian field?
Yeah, it's because I need this island to couple to this without coupling to these two. So to increase the coupling of this island to this island without modifying this, it's like the optimizer found doing this.
I think the other one is cooler.
Yeah, the other one is cooler. It's nicer having computed the capacitance. These two are around the same, but this one is lower. I don't know. Because here the proportion stays, no? I mean, this one it's smaller than this one, but bigger than this one. Here it's the same. This one is smaller than this one and bigger than this one. So they are all smaller, but the proportion between them stays, but here no. So maybe this changes the characteristics. I don't know. We've been running. I mean, I don't have it yet, but here we've been running like taking the values that we have from our design and changing them by a certain amount randomly and computing the characteristics and seeing how the characteristics vary for different degrees of deviation. And more or less you can see that the energy spacing remains the same, the randomicity decreases as we increase the deviation, but up to 200 megahertz, which is not that bad if you have 1 gigahertz frequency. But yeah, this is still, I don't think this is too fair comparison here, because, well, I mean, it's not done yet. Oh.
Yeah, I just curious, is the code, I mean, you are using evolutionary algorithms, general on the communities are using the same, or is it because we find it's
Yeah, the problem of using this kind of algorithm is this, then it is hard to like understand theoretically why it works or why it has the characteristics it has. No, people like take things that know that work, mix them, and try to understand them and make a theory out of it. We are just looking for good characteristics and then look at the circuit. What is this? So it's hard to do it this way if you want to create a really good understanding of the circuit.
in general, they deal with algorithm nodes, they are gonna using evolutionary.
I mean, people don't use too many modes. I mean, the more when it's like 3 modes, they say once a year,
They care more about
they care more about.
following the theoretical.
Yeah.
And related with this optimization method, so what's like the fitness function that you use? How do you decide how do you select the sequence?
Yeah, that's the hardest
Really
part.
the trade-off between the different.
Yeah, that's the hardest part. So, I mean, we've been using like really complex and we've included all characteristics into cost functions, and sometimes the cost function does not work. So it's usually better to choose to focus on certain characteristics that you're interested in. For example, just keep the anonymity and minimize this. And to try to run a lot of times the algorithms, find a lot of circuits who fulfill this, and then rerun the optimization, and now ask for the other ones. Because if you ask everything at the same time, it's like too much for the optimization. It's better to do it like step by step.
The objective optimization to get the right front of different features and so on.
So, I mean, we can talk later, but I have not tried that.
It's not easy to implement this kind of the objective optimization in ways very.
Okay. Okay. Nothing more?
Yeah, only thing that maybe that is very interesting to have some theoretical information about why it works, because usually Pareto Proofs gives you this kind of information about the solutions. Maybe the family of solutions in the Pareto Proof have certain characteristics that is good, and you can go smoothly from all the Pareto Proof. Yeah.
Yeah, but because there's not like a single idea qubit.
Yeah, that's what Mikkel mentioned of looking at these frontiers. It has been done for single mode devices, and people found out that it's impossible to find a single mode device that has at the same time good defacing times, and deposition times, because the requirements conflict for one mode devices. But they have found multi-mode devices who can do that with the 0 pi, which if you make it perfectly, you can achieve this protection. But you need like perfect symmetry, and small mistakes in fabrication like destroys the properties, which is kind of the problem. So that's why we are interested on if this does not match exactly what we want, to keep the characteristics of this to a certain amount. Interesting. Also, if you scale up, you meet and you build a lot of them, they are going to be perfect. Okay.